right, ladies and gentlemen, this is the first lecture in the nomenclature and bonding unit. We are going to be discussing today the ability to determine types of chemical bonds, and we'll also discuss within this lecture writing formulas for ionic compounds and using those formulas to write what we refer to as a molecular, ionic, and net ionic equation. So without any further ado, let's go ahead and get started. Back from your biology days, you probably remember discussing chemical bonds, and you probably have some familiarity with the idea of a chemical bond as being an attractive force that exists between two atoms in part of a molecule. And as it turns out, the identity of the atoms, and more to the point, their position on the periodic table, helps to determine what type of bond gets formed between different types of atoms. And in particular, we're going to be looking at three different types of bonds today, those being ionic bonds, covalent bonds, and metallic bonds. So we'll just go ahead and get started here with the discussion of ionic bonding. We define an ionic bond as the electrostatic attraction between a metal ion, that is a cation refers to a positively charged ion, and a non-metal ion, which we refer to as an anion, which gets a negative charge, in which one or more electrons are transferred from the cation to the anion. Most atoms will have a tendency to fulfill what we refer to as an octet, that is a set of 8 electrons in their valence shell, as they transfer electrons from the cation to the anion. Now note that there are going to be some exceptions to this octet rule, in particular for atoms with only a 1s orbital in their valence shell, that is hydrogen and helium. Both hydrogen and helium tend to fulfill, rather than an octet, instead they fill a duet of 2 electrons, which represents a completed first shell of electrons, because recall, there is no 1p orbital, and therefore we have a full valence shell with just 2 electrons in the s orbital. So let's take a look at a particular pairing that would lead us to see the formation of an ionic bond. To begin here, we'll take a look at a metal atom, like let's talk about an alkali metal here, like sodium, and a non-metal atom, like let's say chlorine. And to begin, let's go ahead and draw some electrons around here. Sodium as a group 1 atom has a total of 1 valence electron, that is 1 electron from the 3s orbital. And chlorine as a halogen has a total of 7 valence electrons from both the 3s and 3p orbitals. So we have 1, 2, 3, 4, 5, 6, and 7 electrons. What I'm drawing right now is what we refer to as a Lewis dot structure, which is a diagram showing the number of valence electrons in the outermost shell of an atom as little sets of dots. And note that we're going to show those electrons as paired off into pairs when possible, recognizing that these electrons tend to form pairs in their orbitals with 1 electron spin up and 1 electron spin down. So we got some structures here representing sodium and chlorine atoms with electrons in their valence shells. Now comparing these two atoms, sodium is on the far left-hand side of the periodic table, and as you probably remember from our discussions of periodic trends, that implies that a sodium atom is a relatively large atom. And it's got a relatively small nuclear charge for an atom within its period, and that valence electron in the 3s shell is a long ways away from the nucleus, meaning that that is particularly loosely bound, and therefore easy to be picked off by other more electronegative elements. Other elements like chlorine. Chlorine being a halogen at the far right-hand side of the periodic table, as we discussed in your periodic trends discussion. Chlorine is a relatively small atom with a relatively large nuclear charge, and therefore is a more electronegative atom. And we could make a prediction here that if I were to take the electron from the valence shell of sodium and move it onto the valence shell of the chlorine, that would put that electron at a significantly lower potential energy level, a more stable energetic position, and therefore a more favorable position for that electron to be in. And as such, by moving the electron from the outermost shell of sodium to the outermost shell of the chlorine, I've actually, from an energy standpoint, made this a better position for that electron to be in. And in doing so, I just completed the octet for the chlorine atom. The chlorine atom now has a total of 8 valence electrons. whereas the sodium has now lost its one valence electron, leaving it with 0 left over, and as such, the previous shell for sodium is now a completed octet. And in doing so, I've just completed the octet rule for 2 of these atoms, and therefore I've formed what we refer to now as a positive and negatively charged ion. That is, sodium has lost its electron, it now has a positive charge. Chlorine picked up 1 extra electron, it now has a negative charge. And by the Pauli-Abdul rule, we recognize that opposites attract, and there's an electrostatic force of attraction that exists between these 2 ions now, which holds them together. And we've just formed our first, what we refer to as ionic bond, in which sodium formed the positively charged cation, and chloride formed the negatively charged anion. Now, note here, guys, that in bonding together sodium and chlorine, we actually formed that bond in such a way that completed the octets for both of the atoms, but the reason why they fill octets is not because it gives them complete octets. There's no magical thing about the number 8 other than the fact that there's 8 electrons within the valence shell of most elements on the periodic table. The real idea is if I were to move more than 1 atom from the sodium over to the chlorine, to move more than 1 electron over, I would actually have to if I were to move more than 1 electron from sodium over to chlorine, the next electron I would take after the valence electron had been taken already would be an electron from the inner core, an electron which was at a very low potential energy to begin with, and therefore would not be at a lower potential energy if I moved it over onto chlorine. And likewise, chlorine cannot gain more than 1 extra electron, because if I were to do so, any additional electrons would have to go into the next shell out, which would put them even further from the nucleus of the chlorine atom, and therefore at a much higher potential energy. So the number of electrons which are transferred from the cation to the anion are governed essentially by where we can put these electrons in their lowest potential energy positions, which happen to be in filled octets. So that is the process of forming an ionic bond. Next, let's go ahead and take a look at the process of forming a covalent bond. A covalent bond occurs when we share electron pairs between 2 different atoms. And again, most of these atoms are going to have a tendency to complete their octet as we share those electrons between atoms. Now, in terms of ionic bonds, you'll notice here that the ionic bond had a tendency to form between a metal and a non-metal, because metals are large atoms with loosely held electrons. Nonmetals are small atoms with high electronegativities, so moving the electron from one shell to the other put that electron in a much lower potential energy, and therefore we tended to see electrons more or less transferred from one atom to the other. A covalent bond happens when electrons are shared between 2 atoms. And we can make a prediction about why we might see sharing rather than a transfer of electrons based upon looking at differences in electronegativities. So if I look at sodium and chlorine, sodium has a very, very low electronegativity, and chlorine has a particularly high electronegativity. So their difference in electronegativity is very large, and therefore the electrons are not shared particularly well between the 2 atoms. But let's take a look, for example, at what would happen if I tried to form a bond between 2 chlorine atoms. Each of those chlorine atoms which have 7 valence electrons. So if I have 2 chlorine atoms, each of which have 7 valence electrons, and I tried to follow the same model for bonding that we just showed for our ionic bond, were I to move the electron from the outermost shell of the chlorine over to the outermost shell of the other chlorine, in doing so, I just took an electron away from a highly electronegative chlorine to give it to another one. And in essence, there's no real energetic benefit to doing so. That electron isn't closer to the nucleus of the second chlorine than it was on the first. And also, as it turns out, there's more of a negative charge around the outside of the second chlorine now, because that chlorine already had 7 valence electrons. Now it has 1 extra one, which would imply, therefore, there's extra repulsion among the electrons within the cloud. So that electron actually is at a slightly higher potential energy being moved over to the second chlorine. And as such, there's no real motivating factor, no energy reason why we'd expect to see the electron transferred from one chlorine to the other to form oppositely charged ions. So the model for ionic bonding doesn't seem to work in this instance. But it would still seem logical that we would see bonds form between 2 chlorine atoms because, as you know, chlorine tends to form diatomic molecules of Cl2. So we need to be able to justify why that might occur. So let's take a look at what happens if we bring these two chlorine atoms close together. If we were to go ahead and bring these chlorine atoms closer together, in moving these chlorines closer together, if we put the two electrons immediately in between those two chlorines right there, you'll notice here that those two electrons in the center are immediately between the two nuclei of the chlorines. That is a position close to positive charge on both the right-hand side and the left-hand side in my drawing, which would seem to us to be at the place of minimal potential energy for those two electrons, that is close to positive charges. So it seems like sharing electrons between two atoms would be a place that would give us the best potential energy position for those electrons to be in, and therefore we expect to see a bond form between those two chlorine atoms there by sharing the pair of electrons. And in doing so, you'll notice that each of the chlorines now has a full set of 8 electrons in their valence shell, completing the octet. So just like in kindergarten when you had to learn what to do when there weren't enough electrons to go around, it seems like the way to give octets to all of the different atoms within a system where the atoms are both electronegative and therefore unlikely to give up their electrons is to essentially share electrons between atoms. And this sharing model of electron bonding is what we refer to as covalent bonding. So covalent bonds would tend to form between atoms which are highly electronegative and therefore unlikely to give up their electrons. So this is going to form between 2 or more nonmetals. Whereas ionic bonds will tend to form between one atom with a very low electronegativity and one atom with a very high electronegativity. That would be forming between a metal plus a nonmetal. Now the big idea here, guys, is this. In terms of these bonding types, ionic versus covalent, for the most part, there really is no purely ionic bonding or purely covalent bonding. All of the different bonds that exist out there really kind of lie on a spectrum between ionic and covalent, based upon differences in electronegativity. If you can imagine, the most ionic bond should be between one atom, which is the most electronegative, that is the most able to steal electrons from other things, and one atom which is the least electronegative, that is the one which gives up its electrons most easily. So that would be a bond between something like francium or cesium and fluorine. So if you can imagine here a cesium-fluorine bond, if I were to look at the differences in electronegativity between cesium and fluorine, cesium has an electronegativity of 0.7 Pauling units, and fluorine has an electronegativity of 3.28 Pauling units, which gives me a difference of electronegativities between these two of cesium has a electronegativity of 0.7 Pauling units. Fluorine has an electronegativity of 3.98 Pauling units. And if I look at the difference in electronegativity between these two atoms, that would give me a difference of 3.28 Pauling units difference, which would be the most unequal sharing of electrons that could possibly exist in a bond. Now, in contrast, the most equal sharing of electrons, that is the most covalent bond we could possibly make, would form between two fluorine atoms, or really any atom of the exact same electronegativity. So, for example, if I had two fluorines, each of which have electronegativities of 3.98 Pauling units, the difference in their electronegativities is a difference of 0, which would imply perfectly shared electrons in a bond between two of these atoms. So essentially what we end up with here is a spectrum of bonding from, on the one side, the most ionic bond you could possibly get, which is a cesium-fluorine or a francium-fluorine bond, where there's a difference of 3.28 Pauling units. And on the other end of the spectrum, the most equal sharing, or the least unequal sharing, where there's a difference of electronegativities of 0 Pauling units. That would be what we refer to as a pure covalent bond, which exists between two atoms of the exact same element, two nonmetals of the exact same element. And every other bond would have somewhere in between in terms of their differences in electronegativities. Now, if you look somewhere kind of in the middle right there, right around at a difference of about 1.7-ish or so Pauling units, is a place where the bonding is kind of more like covalent or more like ionic, depending upon what side of that kind of middle section you are right there. So this is where we call this a position of 50% ionic or 50% covalent character. And that is to say that if the difference in electronegativity is greater than 1.7 Pauling units, the bond is more ionic than it is covalent. If there is a difference of electronegativities of less than 1.7 Pauling units, then the bond is more covalent than it is ionic. But as a general rule of thumb, when assigning whether bonds are going to be ionic or covalent, in general, we can kind of just trust this idea that a metal plus a nonmetal will generally lead to what we refer to as an ionic bond, whereas a nonmetal plus a nonmetal will form what we refer to as covalent bonds. Recognizing that really, all of these different bonds are really positions along a spectrum from purely covalent up to the most possible ionic bond you could possibly have. Now again, there's no pure ionic bond because even in the cesium-francium bond, where the difference in electronegativity is as high as it possibly could be, the nucleus of the cesium atom still exerts some attractive force on the electron which it donated to the fluorine. That is to say, the electron is still, to a certain degree, shared between those two atoms. So, we've got ionic bonds, we've got covalent bonds taken care of. The last pairing we haven't really talked about here is what happens when we have two metal atoms forming a bond together. And not surprisingly, we refer to this type of bonding as metallic bonding. In metallic bonding, we're going to be looking at a bond that forms between two adjacent metal atoms, or really more than two in this case. And if we think about, again, our periodic trends, metals on the far left-hand side of the periodic table are relatively large atoms. And as these metals are relatively large atoms, that means that their valence shell electrons are generally a long ways away from the nucleus. And in particular, because they're such a long ways away from the nucleus, if I look at valence electrons on these metal atoms here, there's really not a whole lot of difference of potential energy if an electron is on one valence shell of one atom or on the neighboring valence shell of its neighbor. That is to say that electrons can essentially be moved from one valence shell to the other with relative ease. And because of that, we say these electrons are delocalized. That is, they don't belong in particular to one atom or another. They're more kind of shared amongst all of the collective nuclei that surround the electron. And as such, because the electrons are attracted both to an atom and its neighbor more or less equally, that implies that what we really see here is what we refer to as a sea of electrons, where those electrons are kind of all washing back and forth and shared between all those adjacent nuclei. And that sea of electrons is what holds these metallic atoms together. And it also accounts for some of the properties which we observe for metals, in particular properties like their conductivity. Because those electrons exist at relatively similar potential energy, depending upon whichever of those two nuclei they're closest to, it requires a relatively small change in potential energy to move the electron between valence shells of adjacent atoms. And as such, the electrons can kind of hop from place to place to place to place without really significant additions of energy into the system. It also explains things we understand about like the malleability of metallic elements. Because if we take these metal atoms and we were to say smack them with a hammer, in doing so, as we smack those metal atoms with a hammer, it might deform the shape of the crystal lattice. However, as the crystal lattice gets deformed, those outermost electrons in the shells of the atoms are essentially just going to kind of just travel along and still be more or less equally attracted to everything all around them as they were before. So those metals, again, are malleable and conductors of heat and electricity because of the relatively loose, delocalized nature of those valence electrons within the crystal lattice. So, three main types of bonding: ionic bonding between metal cations and nonmetal anions, covalent bonding, a sharing of electrons between two nonmetals, both of which are electronegative, to fill the octets, and last but not least, a metallic bond, which is a bond formed as delocalized electrons are shared in a kind of sea of electrons between adjacent neighboring nuclei of metal atoms. So, there's three main types of bonds. And for the rest of this lecture, we're going to focus on the first of those types of bonds which we discussed, that is, focus on ionic bonds. In particular, we're going to look at how we can use electron structures to write formulas for ionically bonded compounds. So, at this point, can you please make sure that you have out a couple of different resources? In particular, I would like you to have out your periodic tables. And as we go through and write these formulas, I want you to be referring to those periodic tables to assist you, because in order to make predictions about ionic formulas, you need to understand electron configurations reflected from that periodic table. So let's take a look at a very, very familiar compound, one which we just discussed in our example of ionic bonding moments ago. If we look at the formula for sodium chloride, we're going to go ahead and look at the valence electron structures of both of these two atoms. Again, we had sodium with one valence electron, and the chlorine, which we said had 7 electrons in its valence shell as a halogen. We discussed that that sodium atom was a large atom with a loosely bound electron. The chlorine atom is small and electronegative. So in transferring the electron from the sodium to the chlorine, we put that electron at a much lower level of potential energy, closer to the nucleus of the chlorine, and therefore this is going to be an energetically favorable transfer to C, moving the electron from the sodium to the chlorine. As we do so, sodium has now lost its electron, giving it a more positive charge now. We're going to label that with a +1 charge as a superscript, indicating that that sodium atom has given up electron. Losing a negative makes the sodium more positive. The chlorine atom, which has picked up that extra electron, now has a full octet. It now has one more negatively charged electron than it had to start with, which means the chloride ion now has a -1 charge. And as I move the electron from the sodium to the chlorine, in doing so, I fulfilled the octet rule for the chlorine. It now has a total of 8 valence electrons. Sodium lost that 1 electron in its valence shell, so its previous octet is now filled, which implies it has also got a complete octet, and therefore an additional transfer of electron either from the sodium or to the chlorine would not be energetically favorable. That is to say, it would either move it from a core shell on the sodium, where it's already at low potential energy, or it would place it on the next shell out for the chlorine, where it's at high potential energy. So in fulfilling the octet rule, all the electrons are in their lowest potential energy positions, and we've now formed a stable compound in which 1 sodium bonds to 1 chlorine to form the ionic compound that you're all familiar with, that is table salt NaCl. Now let's try and apply that same model to a more complicated system now. Let's have a look at the ionic bonding that would form between atoms of magnesium and nitrogen to form the compound magnesium nitride. Have a look on your periodic tables and find the element magnesium. Its atomic number is 12. It's found in period 3 in the alkaline earth metal family. As an alkaline earth metal, magnesium atoms have a total of 2 electrons in their valence shells. And we're going to be bonding this magnesium to nitrogen atoms. Those nitrogen atoms are group 5 elements, and as such have 5 electrons in their valence shells, and are small and electronegative, and therefore likely to take electrons away from the large, low electronegativity magnesium atoms. So let's go ahead and follow the same model we just looked at, transferring electrons from the metal to the non-metal to put them at lower potential energy levels. So I can go ahead and take my electrons and move them from the magnesium to the nitrogen. And as I do so, magnesium has now lost its 2 high energy valence electrons. And I'm therefore unlikely to take a third one away, because that would have to come from a core. So magnesium now has lost all the electrons it's likely to. Nitrogen just picked up those 2 more electrons, giving it a total of now 7 electrons around its valence shell as we move them over there. But there's a trick. That nitrogen still has an additional place where we could put an electron around that valence shell that is still close to the nucleus of the electronegative nitrogen atom. The question becomes, where is that next electron going to come from? And here's where we need to understand that in any real sample of matter, we're not likely to see just one individual magnesium and one individual nitrogen atom. We're likely to see collections of billions of magnesiums and nitrogens. So if we've got lots and lots and lots of magnesiums around, that nitrogen can go ahead and take another electron away from another magnesium atom. And in doing so, we can fulfill the octet of that nitrogen, now giving it a full set of 8 electrons around its valence shell. But you'll see that we're still in a kind of problematic point in which we now have a magnesium atom which has one electron which has not found a low potential energy home around a nitrogen. So just as we did before, we're going to find now another nitrogen atom with 1, 2, 3, 4, and 5 valence electrons where we can donate that extra electron to, putting it again at low potential energy. So we've got now two magnesiums which have lost all their valence electrons, but again we have an extra nitrogen which still has two more positions where we can add electrons around the outside to complete this octet. So you can see where this is now going. One more magnesium atom with its 1, 2 valence electrons can be used in order to complete the octet for that last nitrogen, giving it now those two more electrons. And in doing so, each of those nitrogens has now fulfilled the octet rule. Each of the magnesiums has given up all of their valence shell electrons. And as such, we now have completed the octet rule for all of our atoms, putting the electrons at their lowest potential energy positions. And in doing so, you'll notice the ratio in which magnesium and nitrogen have combined together in is 3 magnesiums for every 2 nitrogens, which gives us the formula of the compound magnesium nitride, Mg3N2. Now, that is a very long and convoluted way of going about and determining the formula of this compound, because the other thing we can consider here, as a way of kind of shorthanding this whole process, is that in moving the electrons from the magnesium to the nitrogen, we've created ions. That is, magnesium has given up electrons, becoming a cation, and nitrogen has gained electrons, becoming an anion. And we know in our compound, magnesium nitride, there is a 0 net charge overall, which implies we can make use of the idea of formation of ions in order to determine the formula without having to go through and draw the motion of all these electrons to fill the octet rules. Let's take a look at how we can do that. Within our compound, we had magnesium atoms, which each gave up 2 electrons. In losing 2 electrons, the magnesium ion would therefore take on a charge of +2. That is, having lost 2 negatives, it becomes more positive. Each of those nitrogens, which had a total of 5 valence electrons to start with, picked up 3 more electrons from the magnesiums to complete their octets, and therefore each of the nitride ions end up with a charge of -3. That is, they have 3 more electrons now than protons. Because we need to combine these two atoms together in a way that puts a 0 net charge on the overall molecule, we can now figure out the smallest whole number ratio that would be formed in terms of bonding these two atoms together that would yield a 0 net overall charge by essentially finding the least common multiple between the charges of those two different atoms. And a shorthand way of doing this is what we refer to as the crisscross method. What we're going to do is we're going to take the charges of the 2 ions, ignore any positives or negatives, and make those charges into the opposite subscripts of our compound, which would therefore give me, for magnesium nitrogen, I would have the magnesium taking the charge on the nitride and crisscrossing it down to the subscript from the magnesium would give me Mg3. And then for the nitrogen, I'm going to take the charge on the magnesium and make it into the subscript for the nitrogen, the nitride ion, with a 2. And again, that gives me the formula Mg3N2, the same formula which we predicted based upon moving those electrons around. And the real reason why we expect this to actually work is because what we essentially have here is the least common multiple. 2 nitrides, each which has a charge of -3, gives me a total negative charge of -6. 3 magnesiums, each which has a positive charge of +2, gives me a total positive charge of +6. So the sum of the positive charges and the negative charges in the overall compound gives me the overall charge on that compound of 0. And therefore, we get the overall formula of Mg3N2. And two more quick examples here, guys. Let's take a look at the compound that forms for species between aluminum and fluorine. Let's go ahead and now skip all the moving of electrons around and just go straight to the end and predict what the overall formula of this compound must be. Finding aluminum on your periodic table, aluminum is element number 13, which is a group 3 element, and therefore has a total of 3 valence electrons. Fluorine is a halogen with 7 valence electrons, and the far upper right-hand corner of the periodic table is therefore highly electronegative. So it's logical to assume that we're going to transfer electrons from the large, loosely held electrons on the aluminum atom to the small electronegative fluorine atom. So if aluminum loses its 3 valence electrons, it would give it, therefore, a charge of 3 positive, and fluorine as a halogen will have the tendency to pick up 1 electron, giving it the overall charge of F negative, a negatively charged fluoride ion. And now to determine the least common multiple, that is the ratio in which aluminum and fluorine can combine together to yield a net neutral molecule overall, I'm going to take those charges on the ions, make them into the opposite subscripts. I can now write the formula of my compound, aluminum fluoride, which would be Al1, but we don't write the 1, it's just implied, F3. That is to say, it takes 3 -1 fluoride ions to balance out the charge of the 1 + 3 aluminum ion. And one final example here for determining the formula of aluminum oxide. Just as we saw above, the charge on the aluminum ion as a group 3 element is +3 when it loses those 3 valence electrons. Find oxygen next on your periodic table. Oxygen is element number 8. It is an oxygen family, not surprisingly, element with 6 valence electrons. And as a small electronegative element, it's going to have a tendency to gain electrons to fill its octet, which will give it a charge as an ion of O2 negative. And again, to determine the formula of the compound aluminum oxide, we're going to ignore any positives or negatives here and make those charges into the opposite subscripts for the atoms, which gives me the formula here of aluminum oxide, Al2O3. And again, you can double check your thinking here. 3 oxide ions, each with a charge of -2, is a total negative charge of -6. 2 aluminums, each with a charge of +3, is a total positive charge of +6. So the +6 and the -6 cancel out. We end up with a net neutral molecule overall. And that is our species, aluminum oxide. All right, so that is the quick way. We call that the crisscross method for determining formulas of ionic compounds. Now next, what we'd like to do is to use our newfound ability to write the formulas of ionic compounds in order to write our very first equation for the year. And we're going to show you how to write what we refer to as molecular, ionic, and net ionic equations describing what happens in a precipitation reaction. And I think the easiest way of going through and understanding this whole process is really just to kind of work through an example together. So what we want to do here is to write a chemical equation describing a process, in this particular example, in which we mix together an aqueous solution of potassium sulfide and a solution of beryllium chloride, mixing those two things together to produce a solid precipitate, which in this case is beryllium sulfide, and an aqueous solution of potassium chloride. And before we get going on the actual equation, we need to have a quick moment to talk about that word aqueous that you see showing up there in our word description of this equation. Aqueous sounds very much like it looks here in terms of the root word here, aqua, which is water. So an aqueous solution is a solution in which we have dissolved a compound in water to form a homogeneous mixture. So when we talk about an aqueous solution of potassium chloride, that really means we've just essentially dissolved potassium chloride in water. Similarly, if you were to describe common salt water is essentially an aqueous solution of sodium chloride, that is salt dissolved in water. Now, as the process of dissolving occurs, it would be helpful for us to understand a little bit about the dissolving process to understand how we're going to go about actually writing these formulas. When you look at, let's say, table salt, which is sodium chloride is an ionic compound made up of positively charged sodium ions bonded to negatively charged chloride ions. And something you probably remember from back in your biology days is that water molecules themselves are polar molecules. Because those water molecules are polar molecules, they have a positive side and a negative side. And as such, they exert attractive forces on the ions within sodium chloride. So if you add salt into water, what ends up happening is those water molecules with a negative side on the oxygen there end up attracting the positively charged sodium ion away from the negatively charged chloride ion. And those ions end up separating apart into two distinct ions, being pulled apart from one another into separate sodium ions and chloride ions. This is a process we refer to as dissociation, and it's essentially how ionic compounds dissolve into solution. Water molecules will surround the positively charged cations and negatively charged anions, and if they can exert a large enough attractive force, those water molecules will pull the ions apart from each other, causing the crystal lattice to essentially separate apart into widely separated ions themselves, which are surrounded by water molecules. We say hydrated ions. Now, understanding that will help us when we get to our second step within this process, so we'll kind of come back to that moments from now. So what I'd like to do here, for example now, is to start by writing ionic formulas for all of the different species which are found within our word equation in the example. So we'll go ahead and look at these. We've got potassium sulfide, beryllium chloride, beryllium sulfide, and potassium chloride. Let's start with potassium sulfide. Finding potassium on your periodic table. Potassium is an alkali metal. As an alkali metal, it has one valence electron, which will have a tendency to lose, being large and a loosely bound electron. And when it loses that one electron, it will give the potassium ion a charge of +1. The sulfide ion is what happens when a sulfur atom gains electrons to form a negatively charged anion. Sulfur is a group 6 element, and as such, it's an oxygen family element. It will have a tendency to gain 2 electrons to fill its octet, therefore giving it a charge of -2. So the compound that would form between potassium sulfide, if we do our crisscross method of determining ionic formulas here, would be the compound K2S for potassium sulfide. Let's apply that same logic to the rest of these species here. We've got beryllium chloride next. Beryllium is an alkaline earth metal. As such, it has 2 valence electrons, which it will lose, giving it a charge of +2. Chlorine is a halogen with 7 valence electrons. It gains 1 to fill its octet, taking on therefore a charge of -1. And if we crisscross those charges, making them into the opposite subscripts, ignoring the positives and negatives, we end up with the compound for beryllium chloride, which is BeCl2. So we have potassium sulfide and beryllium chloride. Last two here are easy because we've already determined the charges here. We have beryllium sulfide, which would be the compound we form from beryllium ions combining together with sulfide ions, +2 and -2, as we just discussed. So we crisscross the charges here, we get Be2S2, but remember we always write an ionic compound as the smallest whole number ratio of the ions present within the lattice. Therefore, we're going to go ahead and just give this BeS, which is essentially the smallest whole number ratio of Be2S2. And then last but not least, we had potassium chloride, where we had K1 positive and Cl1 negative. And again, easy crisscross here gives me just simply the compound KCl for potassium chloride. So we now know the identities in terms of the formulas of all 4 of our different species within this equation. Now, once I've got those formulas written down, the next step here is we're going to turn this now into what we refer to as a molecular equation. The molecular equation shows not only the identities of these species, but also it shows the ratios in which they combine together, and it also shows their states of matter. Following a generic formula in which we start with the reactants on the left-hand side, and we separate those reactants that we started with from the products that we make in the end with a single arrow showing the chemical change taking place. So we separated our products from the reactants with a single arrow. We're going to separate the species on the product side from the reactant side with plus signs. And then we're going to show the states of matter of all the species present in our system. Now please make sure you don't skip this step because this will be important in terms of understanding what happens next when we write the ionic equation. So looking back up at the top, we were told that the potassium sulfide and beryllium chloride were solutions, that is, dissolved within water, implying, therefore, the states of matter of both potassium sulfide and beryllium chloride were aqueous. So we're going to go ahead and designate that with a little parentheses AQ, showing that these things are dissolved within the solution. Beryllium sulfide in the problem was stated to be a solid, that is, this was the thing forming our precipitate. So we'll show its state of matter down here as a solid by putting a little S in parentheses. And then last but not least, Our potassium chloride was also labeled in our word equation as an aqueous species here. And as an aqueous species here, we'll go ahead and label it with a little AQ designated for its state of matter. So we've got the reactants separated from the products. We've got the states of matter of all species. The last thing we need to show in here is the ratio these things combine together in. And in order to do that, what we're really showing here is something you remember from back probably in your science and biology days. That is to say that a chemical equation has to show that we are upholding the law of conservation of matter. That is, in this chemical process, matter is neither being created nor destroyed. And what that really means with respect to a chemical equation is that we're not ending up either getting rid of atoms of one particular type or making new atoms of one particular type, because this is a process in which matter is conserved. And this really comes down to showing our equation as a balanced chemical equation. So if we would like to go through and balance our chemical equation here, just like you did in your earth science and biology days, what we need to do is count up atoms on both sides of the chemical reaction. So on the left-hand side of the chemical reaction, that is over here on the reactant side, I'll have a look here, and I'll start by noticing that I have 2 potassium atoms on the reactant side. On the product side, on the right, you'll notice I only have 1 potassium atom for KCl. And it might seem like an easy fix to just change this formula to K2Cl. However, if I tried to do that, I just changed the ratio these ions are combining together in, which would give me a compound which does not have a neutral charge overall. And therefore, messing around with the subscripts within a chemical formula is something you just fundamentally can't do when balancing a chemical equation. So instead of changing the subscript, instead what we're going to do is we're going to change the ratio of how many of these molecules are combining together. That is to say, we're going to adjust the coefficient. So if I put a 2 out in front, implying that I'm making 2 molecules of KCl as a product, that gives me 2 potassium now on both the products and the reactant side. You'll also notice that I have 1 sulfur on the reactant side and 1 sulfur on the product side, so that's balanced. 1 beryllium on the reactant side, 1 beryllium on the product side, so that's balanced. And now that I've got a 2 on the product side for the coefficient for KCl, I have 2 chlorines on the product side, as well as the 2 chlorines on the reactant side in the compound BeCl2. So we now have a balanced chemical equation showing our overall chemical reaction occurring. And what we have written right here is at this point now what we refer to as a complete molecular equation. That molecular equation has the ionic formulas written in addition to the formulas being written. We also have given the state of matter. And last but not least, we also have balanced our equation to make sure we're upholding the law of conservation of matter. So, we've got a molecular equation written down. But what I want to do next is I want to kind of focus in on what the actual chemical change that's taking place in this process is. And to do that, I'm going to take another step, which is to now write what we call the ionic equation. Recognizing that when we dissolve ionic compounds, that is aqueous solutions, in water, the process of dissolving causes those ions to disassociate from each other. Just like we saw moments ago, those water molecules being polar pull apart the ions into the solution. And as such, a more accurate description of what's really present in the solution is not to say that I really have an aqueous solution of potassium sulfide, because those ions have separated apart. A more complete description would be that I have separated potassium ions from sulfide ions. So what we're going to do in writing this ionic equation is we're going to separate apart, that is, disassociate all of the species which are aqueous in the solution from my molecular equation. And we'll take a look at how that works now in our example. Looking at the molecular equation, I had aqueous potassium sulfide, K2S. Those water molecules in the aqueous solution will pull apart the ions from each other, giving me potassium ions, which again we had as positive 1 charge, and sulfide ions, which we recognized had a -2 charge within that aqueous solution. I'm going to designate their states of matter, again by putting the little AQ to show that they are in fact dissolved in the solution. And last but not least, what I want to recognize here is that in the compound K2S, there were in fact 2 potassium ions with a +1 charge. So I need to put that 2 out in front as a coefficient. Now please be very, very careful here, guys. That 2 goes as a coefficient, not as a subscript. Because as you know, potassium ion has a +1 charge based upon the number of valence electrons it had as an atom. And when it dissociates, those potassium ions separate from each other entirely, giving me two K plus 1s, not one K2 plus 2. Applying that same logic to beryllium chloride. The beryllium ion dissociated in the solution has a plus 2 charge, which is in the aqueous solution. And then again, watch your coefficients and subscripts here. When we dissociate into ions, we end up with two chloride ions, each of which, again, had a minus 1 charge. So we have 2K positive, S2 negative, Be2 positive, and 2 Cl negatives on the reactant side. Now on the product side, here's where we have to pay extra attention. The beryllium sulfide in my molecular equation is in solid phase, which implies this formed the precipitate in the solution. That is to say, it did not dissolve into the solution, and therefore did not dissociate into ions. So anything which is in solid phase within your equation needs to remain stuck together as the compound rather than dissociating into the ion. So we're going to keep the BES together as a solid. And then last but not least, we've got aqueous potassium chloride. So if I have two KCl molecules, that would dissociate into two potassium ions, each of which had a plus 1 charge in the aqueous solution, and two chloride ions, each of which had a minus 1 charge in the aqueous solution. And what we've now got written up on the board here is our ionic equation, showing states of matter, the relative numbers of ions present in the solution, and having disassociated all of those aqueous species, representing how they split apart as they dissolve. Final step, to kind of hone in on the real key chemical change that's taking place within this process. What we want to do is we want to check and see what ions really aren't experiencing any meaningful chemical change over the course of that reaction. If you have a look in our ionic equation, you'll notice that I have two potassium ions with a plus 1 charge, both on the reactant side and on the product side, both which are dissolved in aqueous solution. Which essentially means that over the entirety of this chemical reaction, the potassium ions were there at the start and the finish. Nothing really changed to those potassium ions. They were literally there the whole time, but not actually participating in the reaction. And so those potassium ions are going to get a name which is kind of similar to what you see in terms of people who show up to athletic events who are there but don't actually participate. We call those ions, we call them spectator ions. Things that are present, kind of observing what's going on, but not actually participating. So in order to go from our ionic equation to the net ionic equation, which really shows the chemical change, all I'm going to do is go through and cancel out any spectator ions that are present in the ionic equation. Besides the potassium, there's one other spectator ion present, and you probably can see that now on your notes here. The other spectator ion present in this system is the chloride ion. I have two Cl negatives on both sides of the equation, so I can go ahead and just cancel those out. And what remains behind after I've canceled all that out now is essentially what we refer to as the net ionic equation. That is a most succinct description of what's actually happening in this chemical change. So overall, the real chemical change that's happening, that is the real new bond which is forming, is we're taking that sulfide ion, the -2 charge, which was dissolved within the aqueous solution, combining together with the beryllium ion with a +2 charge, which was also in the aqueous solution. And when those two ions combined together, they formed our product that is the precipitate in this reaction, the beryllium sulfide in solid phase. And this overall net ionic equation really shows the real chemical change that took place, ignoring all those other species that were just kind of happening to be there, but not actually participating. That is the potassium ions and the chloride ions. So, in terms of an overall kind of pathway for how we've gone through and done this entire process, step 1, we wrote out the formulas for all of our ionic compounds. Number 2, we use those formulas to write a molecular equation and in doing so, we checked a couple of different criteria. Number 1, we wanted to make sure that we had all the formulas correct. Number 2, we wanted to make sure that our equation was balanced. And number 3, we wanted to make sure that we had included the state of matter of all of our species. Once we had that molecular equation written down, the next thing we did was we wrote the ionic equation by disassociating all of the aqueous species into their component ions. And then last but not least, the final step to write our net ionic equation, all we did was we canceled out the spectator ions from our ionic equation to yield the overall net ionic equation for the reaction. So that is it for this particular lecture. Thank you very much for listening.